Alright, so in the last video, I think I mistakenly called this radium. This is actually radon. So anyhow, that's alright. So what we're looking for is the bottom numbers, the atomic numbers on this side of the equation add up to what you started with, and the mass numbers on this side of the equation will add up to what you started with. In other words, this number right here, for polonium in this case, is always 4 less, right? Because this never changes, right? Helium always has a mass number of 4. So this number is always going to be 4 less than what you started with, and this number down here, this subscript, will always be 2 less than what you started with. All right, and here let's look at the next one. So this is a beta emission. It's a little different, obviously. In this case, we're emitting an electron which has no mass number. It does have a charge number, so basically it's the same idea again, but notice what's happening is this number, the atomic number, minus 1 will give you what you started with, and notice the mass number doesn't change because an electron doesn't have that. It doesn't have the mass number, which, only if it, this is a subatomic particle, it's not an atom. And then for gamma, it's really simple, and nothing actually changes as far as the mass number doesn't change and the atomic number doesn't change. It just basically is, that this would be radon in an excited state. That's what that asterisk means, and then it de-excites and it emits an electromagnetic some electromagnetic photon, which of course is a gamma ray in this case, and then the nucleus is de-excited and therefore just a plain nucleus. Okay, so those are the three situations, and really it's only the top two that you have to balance. Let's do a couple of examples of that. All right, so let's do an example of an alpha decay. Let's start with plutonium 244. And we're going to undergo an alpha decay. So I'm going to leave some space for the atom that comes before that. So this is going to be plus a helium nucleus. Right, so the helium nucleus. So this is a 2 here, and this is a 4 here. All right, and so if we don't know the atom, we have to look it up on the periodic table. Plutonium happens to be element 94. And since it's an alpha decay, we know that the subscript down here is going to be 2 less than 94. So it's going to be element 92. Oops, I wrote that backwards. So that's 92. And if you don't know what element that is, again, you look it up on the periodic table. And that, of course, is uranium. And what about the mass number? What about the mass number? The mass number is going to be 4 less than what you started with. So it's, instead of 244, it's going to be, so of course it's going to be 240. So that's just another isotope of uranium 240. Okay, so there's an alpha decay. And let's see, let's do another, we'll do a beta decay, and you're going to have some practice with this on the homework. Alright, so let's get some room for our beta decay. Let's start with, let's say we had nitrogen 16. So that's a radioactive type of nitrogen. Nitrogen, of course, is element 7, and we're going to go to some element, right? So this is the nuclear reaction, and we know that there's going to be, it's a beta decay, so we put an electron symbol, so the mass number is 0, and then the atomic number although this is not really the atomic number, more like the charge, is -1. And so right away we know that whatever element this is that the nitrogen's becoming, we know that it's going to be a mass number of 16. All right, because 16, the 16 plus 0 here, the 16 plus 0 at the top has to give us the 16 that we started with, and the same thing goes as the subscript here is always going to be basically one more than what you started with, right? So it's going to be 8, element 8, and because 8 minus 1 is going to give us 7, and element 8, of course, is oxygen. If you didn't know that, you just look that up on the periodic table. And so there is an example of a beta decay, right? Nitrogen 16 becomes oxygen 16 plus an electron. Now remember, this electron comes from the nucleus. It's not, it's quite different than what you would expect, and that in fact changes the atom, right? That's the whole idea of how it changes the atom. All right, let's get back to band stability. So we were talking about how the atom, different atoms on the periodic table can exist. Of course, there's because of this thing called the strong nuclear force. By the way, I should mention this right here. There is a thing called the weak nuclear force. The weak nuclear force is responsible for radioactive decay. That's about as far into that as we're going to get. It's a little more complicated, but that's basically what it does, the weak nuclear force. All right, so the strong nuclear force binds the nucleus together, and the strong nuclear force is found in protons and neutrons. So as I said before, if you have too few neutrons, that's going to cause radioactive decay. If there's too many neutrons, that'll also cause radioactive decay. And so there's this thing called the nuclear shell model that just came from observations of what the nucleus is doing, and this leads us to this idea of band stability. So the band, you're actually seeing the band here. That's this region in purple. And basically what that is the region where between the neutron to proton ratio of 1.5 to 1 and 1.25 to 1. So this region right here is where we find atoms that are stable. And that's only true. So I guess I should go into the whole thing. Between here it is right here. So let's start off. One thing that we know is every element beyond element 83, which is bismuth, every element that has an atomic number greater than 83. For example, uranium or plutonium, thorium. All of those are automatically radioactive. Right, so if you have an atomic number greater than 83, it's immediately radioactive or unstable. That's saying the same thing. Certain nucleon numbers, like for example, these sometimes are called magic numbers. If there has 2, 8, 20, 28, and so forth, all the way to 126, that just adds stability to the nucleus. Okay, so that's for example, helium, right? Helium has 2 protons. Oxygen has 8 protons. So those add stability. Pairs of protons and pairs of neutrons also add stability. For odd numbers of protons and odd numbers of neutrons, tends to be less stable. All right, so this is the way it works. Okay, so again, above 83, automatically radioactive. For atoms 1 through 20, right? If hydrogen through hydrogen through calcium element 20, they have a neutron to proton ratio of 1. For elements 21 through 83, strontium through bismuth, they have to be within the band of stability. Okay, so I think it's easier if I, let me actually show you this. Hold on. All right, so if the atomic number is greater than 83, it's automatically radioactive or unstable. That means the same thing. All right, so for elements 1 through 20, so atomic number 1 through 20, hydrogen through calcium, you have to have a neutron to proton ratio exactly equal to 1. Okay, that makes those atoms stable. Now for elements 21 through 21 through 83, you can have a band, a range, if you will, of stability. So the lower limit of the range is 1.25. So that's the lower limit, and it's the neutron to proton ratio. And the upper limit is 1.5. So 1.5. All right, so we'll do examples of those. I think that's the way to predict whether an atom is radioactive or not. So we'll do some examples. Let's see. All right, so the first thing, here's our first example, calcium 43. So calcium, you look on the periodic table. If you don't know this, you're not expected to know this. This is why we use the periodic table. Calcium's element 20, and I mentioned that earlier. And so we can figure out the number of neutrons. That's very important to do. And also the fact that it's element 20, we're looking for this, right? Let's be very specific about this. We're looking for a neutron to proton ratio of 1, exactly equal to 1. And you can already see it's not going to be, but let's do the calculation anyway. So the number of neutrons, this is exactly the way we did these before, is going to be 43 minus 20, which of course is 23, right? If it was stable, it would be calcium 40, of course. We'll do that as an example in just a moment. All right, so we have the neutron to proton ratio. Neutron to proton ratio. You actually have to do this calculation to prove this is going to be, is going to be 23 divided by 20. And that's clearly not 1. I'm not exactly sure what it is. We'll do that in our calculation. So I get 1.15, which is clearly greater than 1. Right? So what we would predict is calcium 43, this isotope, is radioactive. That's the way this works. All right. For example, what about calcium 40? Right? If just do a quick calculation, the number of neutrons for calcium 40 is going to be 40 minus 20, which is 20. And now if we did the neutron to proton ratio, it's 20 neutron to proton ratio. It's 20 divided by 20, which is exactly 1. So that one, calcium 40, we would predict to be stable, very stable. All right, we'll continue this in the next video.